Alrighty, gang, we're going to show how Gibbs energy changes with pressure, so the pressure variance of Gibbs energy, and we're going to do that using a common exam problem. And this is it right here. What is the change in Gibbs energy for liquid water? So we're going to deal with a liquid, not a gas, when it's compressed to 1,000 bar. And we're given the density of water at 298 Kelvin is 0.997 joules per centimeters cubed. So to show how the Gibbs energy changes with pressure, we can start off either using this equation, which you might have seen in class, or using the fundamental equation of chemical thermodynamics, which is dG equals VdP minus SdT. G is Gibbs energy, and S is entropy, not enthalpy. Now, this is a constant temperature process, so dT is 0, and if we multiply this equation on the left by dP, we'll be left with the same equation here. So that's what we have, and we'll integrate both sides. The integral of dG is G from initial to final, so that becomes delta G. And on this side, we're going to assume that volume is constant, which it pretty much is for liquids and solids. And we're only compressing it to 1,000 bar, which isn't very much, so the V gets yanked out of the integral. We're integrating dP, which is P, and we're going from P initial to P final, so that becomes delta P. And then we'll also assume that we're dealing with molar quantities. So I hope that's not too much of a jump. The left-hand side becomes delta G. The right-hand side becomes V because that's a constant times delta P right here. And we'll assume we're dealing with molar quantities. We just take everything divided by the amount of moles right here. Now, we have the molar volume, but we're given the density. So to convert the molar volume into the density, we can use this nifty equation. You may have another way to do it. Molar mass divided by the density. If you do that, you have units of volume over moles, which is what we want. So if we plug that into here, we basically have everything we need. So we can plug in our numbers. This is the molar mass of water. This is the density in which we're given. This is our change in pressure right here. If we plug this into our calculator, 18,051 centimeters cubed bar per mole, which is our answer, but not in the units we want. The Gibbs energy is usually in joules or in kilojoules. So to get this to joules or kilojoules, I actually first I'd like to convert this into SI units or SI-like units. So this is my favorite conversion here. We can convert the bars into pascals and the centimeters cubed into meters. And if we do that, everything cancels except for Pascal meter cubed and the moles, of course. And I kind of know, and it might be on your conversion sheet, hopefully you have one, that a Pascal meter cubed is equal to 1 joule. So therefore, our answer, the change in molar Gibbs energy, is 1,800 joules per mole. I rounded to 2 sig figs. I know we have 3 sig figs here, but this is kind of like 1 sig fig, so I thought 2 would be good. And a subtlety that I think is important, notice the question just asked for delta G. So technically, this is the absolute change in Gibbs energy, which depends on the amount of water, but the answer is in molar quantity, the change in molar Gibbs energy, which is all we can get because we don't know how much water we have. So sometimes on exam problems or textbooks, they say delta G, but they really mean the molar quantity of delta G. You can convert this to kilojoules per mole if you want. All right, y'all, good luck on your midterms, final exams. I've got tons and tons of other videos on thermodynamics and other aspects of chemistry, physics, and math, and I'll see you in the next video. Cheers.